Everyone, I'm Shuming. I'm from McMaster University in Canada. So my research topic is about wearable speed limit control for smart work zone with connected vehicles. So freeway work zone with lane closure can cause traffic disruption and with conjunctions with increased travel time, safety risk, and emissions. And variable speed limit control system has been developed. As you can see from the figure on the left, we have the static speed limits, and by using the traffic sensor, the detection from the traffic sensors, we can generate a dynamic speed limit to mitigate the negative impact of work zones. So when it comes to traffic sensors, there's one scenario in this figure. You can see there's a queue already building up near the work zone areas, and then queue start propagating upstreams. But when we have two set of sensors, the traffic sensor number one, which is located upstream of the work zone, give us a signal saying right now is a free flow with no congestion. And the second set of traffic sensor, TS2, is telling us, yes, it's very heavily congested, and which sensor we should use and how we can calculate the speed limits upstream of this work zone. Therefore, this is the objective of my study, to develop a VSL control system to provide reliable traffic condition and improve the traffic conditions using VSL control. From this system framework, there we have this VSL controller, which would generate dynamic speed limits to influence the traffic on the freeway corridor. And then the traffic sensor will detect the traffic densities, the traffic density from the distant upstream traffic sensor, and also the density from the merging area sensor will be fed into these weighted density components. And these weighted density components will using the speed and the location of the connected vehicle to calculate these weights, which would be, and then we'll find this weighted density. And then the error between the critical density and the weighted density will be fed into this VSL controller to generate the dynamic speed limits and again influence the traffic on the freeway corridor. So from this system framework, we mainly have two components. The first part is about weighted density. The second part about the VSL control. Now let's talk about the first part, weighted density. So the weighted density is calculated by assigning a weight between the two traffic sensors. Traffic sensor, which is at the merging area, and the traffic sensor, which is at the distant upstream in the work zone. And how we can calculate this weight, and we use the kinematic wave theory from the transportation areas. And this weight will use two lengths. One is L1, which is determined by the connected vehicle, and L2, which is determined by the distance between these two sensors. When we talk about the L1 can be processed by using a connected vehicle. And that connected vehicle needs to satisfy two requirements. The first one is the travel speed need to be below a certain threshold so that we know the traffic is already under congestion. And the second condition is it should be at the furthest upstream of the work zone. So by using these two formulas, we can calculate the weighted density. Now the second component is about VLCL control. So the VLCL control is using the error between the critical density and the weighted density. And this error can be used to calculate a factor called beta. And this beta be timed to the speed limit of last time step to get to the speed limit of current time steps. So right now we talk about two components in the system framework. Now we have built the system and calibrate and validate the system in a simulation environment using the realistic traffic measurements from the California Freeway database. And this is a realistic work zone happened in 2018. And we tested that system for 1 hour and a half under different traffic demands. So the traffic demands will be low first and then go up and then go down again. So we test the four scenarios. The first scenario is without any VSL control. The second scenario is we have VSL control, but only with distant upstream sensors. And third one is with sensors at merging area. And the fourth one is the one proposed in this study. So as you can see from these four figures, when it comes to no control scenarios, the traffic density jump way high when the traffic demand is very high. And one can look at the second scenarios because the traffic sensor is very close to the merging area. That's is at the distant upstreams, the work zone area. That's why there will be a lag to detect the traffic congestion. And the third scenarios, the traffic detection is overestimated compared to the real traffic density. And the fourth scenarios, we can track the actual traffic density and maintain that density at the critical density, which will help us to maintain the maximum traffic flow. And from this spatial temporal contour plots, and those dark area, those dark or red area represent congestion areas. So the first one you can see is super congested, but second and third scenario will also have a congestion, more congestion area compared to last scenarios, as you can tell. And which can also tell from the statistics numerical results. Our proposed system has the best performance in travel time, emissions, fuel consumptions, and the time to collision, which is one of the safety factors. So in summary, the design system can provide reliable and accurate traffic state estimation, and this VLSL control system can improve traffic conditions for VLSL for freeway work zone, and also it inspires the work zone planners. They may need to think about the impact the sensor locations when they are trying to implement the traffic control systems. That concludes my presentation. Thank you.